Hi class, Dr. Searcy here with the video lecture for the textbook for Chapter 4. And as you're seeing, the title of the chapter is Variability. I thought I'd begin by going ahead and giving you guys a definition of what is meant by variability in statistics. Here we're saying that it is referring to the differences between scores in a distribution. To further explain this, I want to begin with just a bit of a review of what we've talked about so far in this class. Right, so far we've been talking about how the whole purpose of these analyses is that some researcher has just conducted a study, and they've collected data in that study. So say, for instance, a researcher's gone out, conducted an experiment, and here is the data that they have collected, maybe a set of X scores. We could say that maybe they got a 1, a 2, a couple of 3s, and a 6. And in this example, we're saying that maybe this is that kind of study where a researcher conducted an experiment on some patients who were clinically depressed, right? So they used the independent variable of administering this new antidepressant to measure the dependent variable of the effect of the antidepressant on the person's mood. So the dependent variable scores that we're getting here are these, let's call them happiness ratings, right? And we've been talking about this in terms of like that scale of 1 to 10 where the person tells us how they're feeling. Maybe in this case, because we're talking about happiness ratings, we could say that a higher score is indication of being happier, and a lower score is an indication of being less happy. This doesn't look good, because what that means is, what I'm seeing here is that it looks like the medication has been not that effective with most of the participants, right? The only person that's got a really high happiness rating here is this person who gave them a 6. In any case, the researcher wants to evaluate this data, right? So as we've been talking about creating the data in terms of distributions, we've said that the researcher can take the data and place it into a distribution table, right? And the purpose of this is to organize the data so that we can summarize it. So let's just make sure that we remember this is a table. And we're using it to organize the data. From here, we've said that a couple of ways that we're going to start to organize and summarize the data is once we've got it stacked up, we're also going to calculate the sum of the data, or the sum of the X scores. In this case, that sum is 15. A second thing that we want to get is how many participants were in the study. Here we're saying that since this is a sample, that our sample size was 5 participants. And then a third thing that we've been, a bit of information that we've been getting about the data is that we also want to know the average X score for the group. And the way that we're going to articulate it is we're going to refer to it as X bar, right? X bar represents the mean of the sample. And the way that we've organized everything is it's really easy to calculate the mean here, right? Because remember, the mean is the sum of the data divided by the number of participants. In this case, that means that the mean is 3. Another thing that we can do to the data to understand it further is to create another column of data where we now are looking at taking each X score and subtracting the mean from that score, right? So taking each one of these scores, creating a row where we've got some new number where we've subtracted the mean from each X. Let's see what kinds of values that would result in this example. Here we're saying that 1 minus 3 is negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0. 3 minus 3 is 0. And 6 minus 3 is 3. So at this point, we now have started to give ourselves a sense of the understanding of the variability in this data, right? So we refer to variability as the differences between the scores in the distribution. The way that we've got this is we have a sense of the differences between each score and the mean of the set. When we do this, we say that we are calculating something referred to as deviation. Okay, so this mathematical expression is deviation. What do we mean by this term deviation? Well, to define it, it's where we say that we are calculating the difference between a number in the distribution and a fixed number, in this case, x bar. Okay, so let's just kind of go through this just to make sure that we got it. First, let's note that we're calculating a difference, right? So it's a subtraction problem. What are we subtracting from what? Well, we're saying that we're taking the number in the distribution and we are subtracting some fixed number from it, in this case, the mean of the sample. And when we do this, it gives us a sense of how far each score is from the mean of the group. Now, to really kind of understand the purpose of doing this, the thing I want to do is show you a second hypothetical set of data, right? So we've hypothetically collected this data to see how the people reacted to the antidepressant. Let's see this set of data instead. We can say that we're looking at exactly the same kind of thing, but instead of getting these scores in terms of the effectiveness of the antidepressant, we got these scores. As we look at them, we see, interestingly, that the scores summarized are very similar to the previous set of scores. For instance, we still have a sum of x that adds up to 15. We still had 5 participants in the study, and the mean of the group is still 3. However, an interesting difference starts to show up when we go to calculate the deviation within this group. And it looks like this, right? So now we've got these numbers by saying 2 minus 3 is negative 1. Here we got a bunch of 3's minus 3, so that's why we got these zeros. And then down here we have 4 minus 3 equals 1. Let's compare these deviation scores to these deviation scores. One thing that I want you to notice right off the bat is that it looks like there is more variability here than there is here. How do I mean that there's more variability? Here you have larger deviations, right? You got this negative 2, and you got this 3. Here, you've only got zeros and ones. So what that means is that here you have what we would refer to as more variability. And here you have less variability. Okay, this is important to the researcher because it gives the researcher a sense of how trustworthy the data is, how accurate it might be. How are we getting that? The way that we're getting that is here we would say that each individual score, because it has more agreement with the mean, right? It's less further away from the mean than these scores are. There's more similarity amongst the participants in this group than there is in this group. So thinking about how effective the drug was, right? Here you have a more consistent effect of the drug occurring than over here. Over here, this person got very happy under the effect of the drug. This person got very happy under the effect of the drug. This person was less happy under the effect of the drug. But here, everyone was pretty much affected similarly, right? They all reported a similar happiness score. Now, if we're talking about studies and a researcher is going to collect some data, which set of data would the researcher rather have? The set with the more variability or the set with the less variability? We'd say that the set with the less variability is the set of data that is more desired, just because there's that consistency amongst the scores with the participants. Okay, so from here, another term that we can talk about is the range. The range can be defined as simply taking the largest score and minusing the smallest score from it. Maybe, for example, we could say that for the first group that we talked about, we went and found their largest score, and it was this 6. For that same group, we also went and found their smallest score. It was that 1. And so to find the range, we're saying 6 minus 1, and then that means the range is 5. For the second group, the largest score was 4, and the smallest score was 2. So here, the range is 4 minus 2, or 2. Now again, range offers a sense of what's happening with regard to variability in the set of data. One thing that we can see from here, or that we can infer from here, is that a data set that has a larger range also may have more variability. A data set that has a smaller range also may have less variability. But then continuing to talk about this idea of variability, one thing that researchers are going to want to be able to do is really get into measuring how much variability is present. And the way that that's accomplished is by calculating sum of squares, or sum of squared deviations. So what is the sum of squared deviations? I'll go ahead and offer a definition here. And I'm going to offer the definition in terms of mathematical expression, using terms that we are familiar with at this point. And I'm just going to go through them, right? So one word in this term is deviations. We already have an understanding of what a deviation is. We've been talking about deviations being this x minus x bar. So that's what we have here, this x minus x bar. But we notice that it's inside of a parentheses, and on the outside of that parentheses is a square, an exponent of 2, right? So that's the squared part right there. And at the left side of this expression, we've got our uppercase sigma, which refers to sum. So what we are saying here is that we have, in this expression, the sum of the squared deviations. And that's what we're going to be looking for. You may have noticed that when I first introduced this term, I referred to it as sum of squares. And the reason why is because it's an often used nickname when referring to this measure. So, how does one go about calculating the sum of squares, or the sum of squared deviations? Well, to answer that question, I first need to note that there are 2 different ways to do it. We can calculate sum of squares using the definitional formula, or we can calculate sum of squares using the computational formula. I'll take a quick moment to explain how both formulas work. To begin with, we'll talk about the definitional formula, and you'll just note that it starts off by us doing exactly everything that we've been talking about so far, right? So a researcher goes out, collects a set of data. This is a new set of data that we're using here. They take it and they organize it in terms of a table. Once they have the table created, they then calculate the sum of x. In this case, it's 8. They get a sense of how many participants were in the study. Here, we're saying that it was 4 participants in the study. And then they use those 2 values to calculate the mean score of the group. In this case, 8 divided by 4 is 2. So now remember that the whole goal here is to calculate this sum of squares, or sum of square deviations. So the next thing that the researcher is going to do is create that deviation column. Okay, so just to make sure that you're understanding how the deviation column works, we'll explain how we got these numbers. We got 1 minus 2 is negative 1. 0 minus 2 is negative 2. 6 minus 2 is 4. 1 minus 2 is negative 1. Now from here, you may already be starting to see what our next column is going to be. It is going to be where we create that squared deviation. And we're going to do it this way. So we're saying we're taking our column and we're just squaring all of the values inside the deviation column, right? So it's a 1 here because it's negative 1 times 1. So then we got negative 2 times negative, oh, I'm sorry, let's say that again. This 1 came about by saying negative 1 times negative 1. So then we have negative 2 times negative 2 equals 4. 4 times 4 is 16. Negative 1 times negative 1 is 1. From there, we are now able to create our sum of squared deviations by simply adding up the column. And we see that for this set of data, the sum of the squared deviations is 22. Another way that we can refer to the sum of squared deviations is by using the abbreviation SS. SS standing for sum of squared deviations, or sum of squares. In either case, we're seeing that the number or the value for that is 22. Okay, so you may just want to notice why this is called the definitional formula. Basically, it's called the definitional formula because we're using a mathematical formula to create a value that is the definition of the term, the sum of squared deviations. I'll note, though, that sometimes using this formula is impractical. It can get kind of complex and hard to do, especially when you're using decimal values, which happens a lot when researchers are working with data. For that reason, researchers often will use the computational formula instead. It's just a quicker, easier way often to get the sum of squares value. So how does the computational formula work then? Well, here is the actual formula itself, right? So the sum of squares computational formula is where we find the sum of x squared and we subtract from it this division problem where the numerator is the sum of x in parentheses squared divided by n. So let's take the data that we've got over here on the left side and use it to calculate our sum of squares computational formula. To start with, we create the column just the way that we've been doing in the past. One thing that you might notice here is in this form of the equation, in the computational formula, we do not necessarily need to calculate the average of the sample scores. The reason why is we're not going to use that in the formula. Instead, the next step would be to now create a column of x squared values, right? So we're calling this column x squared, and we're doing exactly that with each x value in the column. We're saying 1 times 1 is 1, 0 times 0 is 0, 6 times 6 is 36, 1 times 1 is 1. We then add that column up to get this sum of x squared value, ends up being 38. And so now we have all the information that we need to punch our numbers into the computational formula. So let's see how that's going to work. So here is the generic form of the formula, and here are the numbers that we're going to punch in to fill out that generic form. So it begins with this sum of squares equals 38. Where did that 38 come from? Well, it's this sum of x squared, so it's that 38 right there. Then we're going to subtract this numerator, the sum of x in parentheses squared. What number is that going to be? That's going to be an 8 inside the parentheses. Why an 8? Because that's our sum of x over here. And then we have a 4 in the denominator because the 4 is the number of participants in the study. From there, we can simplify our equation, where first we want to get rid of the exponent and see what the value is after we remove the exponent. So it ends up being 38 minus 64 divided by 4. Thinking about the order of operations in this problem, the next thing that we're going to do is the division problem. So then we end up with 38 minus 16. From there, it's a simple subtraction problem where we get 22. Now, one thing that you might want to notice is that we've got the same answer in both formulas, right? And so that's what we're saying. These are two different ways to get at the same thing. Both are giving us the sum of squared deviations. Okay, so now what do we do with that information? Once we've calculated our sum of squares, where do we go from there? Well, the sum of squares is going to be some valuable information that we're going to use in some of the next terms that we're going to describe. Beginning with variance. Just to start off with, right, so we're talking here about how widespread out the data is or how similar the data is. First term that we've used to do this was variability. Now we're continuing to do that with this new term, variance. So what is variance? Variance can be defined as simply the mean of the squared deviations. So what we're saying here is that we have been going out and we've been finding out what each squared deviation is. Now we're going to figure out a way to calculate or to average those squared deviations. And the way that we're going to do that is by calculating variance. Now, just to begin here, one thing that we need to note is that when we go to calculate variance, we have to pay attention to whether we are working with population data or sample data. Let's remember that a population is everybody in a group that you're interested in studying. What we've been saying, though, is that oftentimes a researcher does not have access to an entire population. When that's the case, they're going to pull a sample out of that population and evaluate everybody in the sample. However, there is a formula for this just in case the researchers are able to contact everyone in the population. Okay, so let's first talk about how a researcher would do this, how they would calculate, let's say, population variance first. And I want to start first by noting the symbol that we use to denote population variance. So here we've got a brand new symbol that we're introducing to the class. This symbol represents population variance. First, I just want to note that what we're doing here is that we are now introducing another letter from the Greek alphabet at this time. And so since we're doing that, I want to take a moment to just kind of review what Greek letters we're already using. By the way, you do not have to write this down in your notes. I'm just offering this as extra information. But let's look. Maybe like going in order of all the letters that I presented to you guys in the class. I think the first letter that you have come across in this class is the uppercase letter Psi. Right, and you saw this when you first went to the class homepage. The reason why that symbol is there is because the uppercase letter Psi is the letter that we in psychology use to identify our field. By the way, I guess I should also note that when we look at this Greek alphabet, we're also seeing that just like in the alphabet that we use, there is a uppercase version of each letter and a lowercase version of each letter. The reason why I'm pointing that out is because the next letter that I think that I introduced to you guys was the lowercase mu. I wonder if anyone remembers what I said lowercase mu was. Just in case you don't, this was the symbol for population mean. But then another letter that I've talked about so far this semester was this uppercase sigma, right? And the thing that we've been saying uppercase sigma represents is sum of, right? Been doing that all this time in this lecture, by the way. Okay, so now time to talk about the new Greek letter that we're introducing here. This new Greek letter, as it turns out, is another sigma, but this now is the lowercase version of sigma. So I'll just go ahead and call this population variance. And just note if squared. Okay, so let's get back to the lecture. Remember, you don't have to write down the Greek alphabet. I'm just using it to kind of show off the fact that we are using the Greek alphabet, and I think it's kind of cool. But let's find out how we would use our data to calculate population variance. So first, we're saying that we use the symbol sigma squared, or lowercase sigma squared, to identify population variance. The formula that we would use to calculate it is sum of squares, right? So that value that we've just been talking about calculating, divided by n, the size of the population. In the example that we had just been using here, we're saying that the equation is going to be 22 divided by 4, right? Regardless of whether we use the definitional formula or the computational formula, in either case, we got a sum of squares of 22. So that's why we have 22 here. And in that sample, the n was 4. And so that's why we have 4 there. So as we see, to calculate population variance is just a simple division problem. And we end up with a population variance of 5.5. Okay, now though, we need to talk about, but what if we need to calculate sample variance? By the way, of the two types of variance that we ought to be calculating, here I've been referring to this data as sample data. So this would be the more appropriate equation. First off, the symbol that we would use this time is now lowercase s squared. Lowercase s standing for sample. And just knowing that it's the mean of the squared deviations. But the formula this time is now going to be sum of squares over, another new term, df. What is df? Well, as it turns out, df stands for degrees of freedom. And all this means is, it's kind of like an instruction. It means that you're supposed to take whatever your n is and subtract 1 from it. So in this case, our sum of squares was 22. Our sample size was 4. So our degrees of freedom then is going to be 3. Right, so this is the mathematical problem that we're going to calculate. From here, it's just, again, a simple division problem, and we get a sample variance of 7.3. But there are other ways of measuring variability that we need to talk about. Another way that's really important is standard deviation. What is standard deviation? Well, that is the square root of the variance, right? So we've just calculated variance. Standard deviation is simply going to be the square root of that number. The reason why we're calculating this is because it's going to give us this very important measure, what we're referring to as the standard distance from the mean. So I'll explain what I mean by this in just a moment. Before we do, let's go and talk about the mathematical operation that's going to be involved here. So as it turns out, when we go to calculate standard deviation, we run into the same issue that we do with variance. There's a formula for population and there's a formula for sample. Okay, so we can calculate either population standard deviation or sample standard deviation. To begin with, let's go ahead and see how we would calculate population standard deviation. First, let's just note that the symbol that we're going to use this time is just simply that lowercase sigma. The reason why we're just using the lowercase sigma is because we're taking the square root of the variance. So what's the formula for this? Well, it's exactly the formula that we had before, except under the square root symbol. So when we go to calculate, we have the same numbers. They're just going to be square rooted. So it's going to be the square root of 22 divided by 4, which is going to equal that 5.5. But now we have to calculate the square root for that, and it ends up being 2.35. So then when we go to calculate the sample standard deviation, we kind of have to follow the same rules that we did with sample variance, and now also include this new thing that we're doing with standard deviation. How do I mean that? Well, with the sample standard deviation, we're still talking about using this lowercase s to represent the idea that we're talking about a sample, but we're no longer squaring the s, and the formula for this is going to be the square root of 22 over 3. Right, so basically, it's going to be the same numbers that we used when we were calculating variance. It's just that everything is under the square root. Let me make sure that you understand that. So the formula for sample standard deviation is the square root of sum of squares divided by degrees of freedom. Right, so that's how we have this 22 divided by 3. So then we go to solve that mathematical expression, and we see that we have now the square root of the 7.3. We have to solve for the square root, and so we find that our answer is 2.7. Okay, now from here, one thing that we need to do is really start to gain a sense, though, of an understanding of what standard deviation is. Beginning with this idea that standard deviation is going to be this measure of a standard distance from the mean. This is something that we're going to be talking about a lot in our future chapters to come. So I really want to take this moment to just prepare you for how we're going to do this. First, let's note that another thing that we've been talking about all semester long is the histogram. What we're going to end up doing is we're now going to combine our understanding of how the histogram works with a sense of how standard deviation works. So first off, I'll just kind of remind you of what a histogram is. A histogram is a type of bar chart. It's not a bar chart, right? Because remember, a histogram is a chart where the bars are touching. A bar chart is where they don't touch. And also, a histogram is where you can show the interval or the ratio data. So we've been looking at this example quite a bit so far this semester. You might remember they're organizing the data that they used to organize the data. And so I'm just realizing that that is not right. Anyway, I forgot that I have to do the multiplying of the x's and the f's. So I'm just going to leave that alone for now. But another thing that we've been saying when we look at histograms is we've been saying that we can draw that curve above the histogram. In this case, this curve looks like it's going to be a normal curve, right? A curve that is symmetrical, and that then means that the mean is going to be right at the top of the curve. One thing that you're going to want to start to see with this is that we're going to be using histograms to express standard deviations. And so I want to give you a sense of how that's going to work. Let me ask you to take a look at this curve. So this is a curve showing different standard deviation units. Okay, and the way it works is, let's say that we had a number line at the bottom of this curve. And the numbers in the number lines are going to be different standard deviation units. Okay? Let's say, first of all, that the line in the middle, just like we noted up here, is going to represent the mean of the group. When we draw that line in the middle that represents the mean of the group, we want to assign a standard deviation number right under that. And that standard deviation number is 0. Why are we using the number 0? Well, because let's think of what a standard deviation is, right? A standard deviation is a standard distance from the mean. If on this line we're saying the mean exists, then the distance away from that mean is 0, right? There is no distance away from it because that's where the mean is. So then what the researchers are talking about with this standard distance is moving away from the mean, either to the right, in a positive direction, or to the left in a negative direction. And with that, they're saying, as you move away from the mean, we can talk about moving away from the mean in terms of a standard distance, a standard or equal distance. And so that's what we're looking at here. First, let me just note what these numbers are saying inside the curve. This is saying, like, say for instance, this area here, how much of the data is contained in this area, right? So here you're saying 34.13%. What that means is that if we look at the data in terms of the histogram, the chunk of the histogram right here contains that amount of the data, 34% of the data. Same thing with this area of the chart as well, 34% of the data. So if we were to combine those two dark areas, we could say that there's about 68% of the data contained in this chunk. Notice what's happening is as we move away from the mean, there was less data the further that we get away, right? So, for instance, for this chunk right here or this chunk right here, here there's only 13%, and here there's only 13%, right? And you're seeing that reflected here in the height of the bars. Then, as we move away even further, we're seeing that there's even less of the data contained in this section or in this section, until finally we move out even further and there's almost no data there. Okay, so we're saying that we can figure out for any set of data some standard distance away from the mean. And that standard distance is going to be in terms of these chunks. So we got a chunk here and a chunk here. We refer to this chunk and that chunk as a standard unit. And so we could put a tick mark here and here. And we could say that whereas the 0 represents not being away from the mean at all, if we put a 1 here and a 1 here, now we're saying at this line, we are one standard deviation unit away from the mean. And here, we are 1 standard deviation unit away from the mean. Then, we could do the same thing at the next boundary. Here and here, we've now moved 2 standard deviation units away from the mean. And then the logic can continue all the way out, right? So here's the next boundary. And at that next boundary, we have now moved 3 standard deviation units away from the mean. Right, let's just make sure I got this right. So we started out at 0. As we moved away, we got to 1 standard deviation unit, now 2 standard deviation units, now 3 standard deviation units. Same thing on the other side. 1 standard deviation unit, 2 standard deviation units, 3 standard deviation units. Okay, so that's standard deviation. One thing that you're going to notice in future chapters is I'm going to really start to have you guys look at histograms and see the curves under the histograms. When I do this, I'm going to start creating these kinds of number lines under these histograms. And I'll probably have like a triple type of set of number lines. A first one can be the set of x values, right? So that's how we started off since the beginning of the semester. We've said that each number on the horizontal of the x-axis is a number representing the range of x values. Below that, however, we'll be saying that there is a second row that we'll be using. And that second row is going to be now where the mean is, right? And the way that we're going to say that is we're always going to say that the mean is some number, and that mean is going to be right in the middle, right? So some average that's in the middle. But then from there, we're going to say that there's going to be a third row that we're going to always talk about underneath the histogram. And that third row is going to be that standard deviation. And the logic is going to stay the same as we do that. Right under the mean will be that value of 0. Then as we move away from the mean, we'll have a standard deviation unit of 1 that we've moved and a standard deviation of 1 that we moved on this side. And then as we move out further, then a standard deviation unit of 2, and so on. Okay. So that's everything I wanted to say about the Chapter 4 textbook. I look forward to seeing you in the odd problems for this chapter.